From the moment 3I Atlas was detected, astronomers focused not only on its trajectory, but also on its composition. The fact is that observations using spectral analysis revealed the presence of basic ices, water, carbon monoxide, and traces of other simple molecules. This is consistent with many comets originating in the outer reaches of star systems. Yet Atlas's exact proportions differ from any known solar system object. The relative abundance of certain molecules, like carbon monoxide compared to water, appears unusually high, suggesting it formed in a colder or more distant region than typical comets. Some researchers interpret these ratios as evidence that Atlas has spent millions of years traveling through interstellar space, preserving volatile compounds that would otherwise sublimate near a star. This explanation fits with current models of long-term cosmic cold storage. Yet subtle anomalies remain. For instance, the dust-to-ice ratio in Atlas seems unusually low compared to other comets. While some suggest observational errors, multiple independent telescopes confirm the measurements, lending credibility to the peculiarity. In the scientific community, whispers have circulated about the object's apparent structural uniformity. Unlike many comets that fragment as they approach a star, Atlas has remained surprisingly coherent, showing no signs of substantial breakup even as it neared the Sun. Some suggest this could indicate a particularly dense or unusually solid composition. Others, speaking anonymously, hint at a more speculative possibility, that the internal structure could have been deliberately consolidated, perhaps as a way to survive long interstellar travel. No direct evidence supports this, but the observation alone is striking. Adding to the intrigue are the traces of exotic molecules detected in faint spectral lines. These molecules, while chemically plausible, appear in ratios and distributions that differ from solar system norms. Some chemists argue that these differences are the natural result of formation in a star system with different elemental abundances. Others suggest quietly that these compounds could hint at processes we do not yet fully understand, or that Atlas may have encountered unusual environments before entering our system. The data are incomplete, leaving room for interpretation. Observation logs provide further mystery. Some early data sets on Atlas's composition were temporarily unavailable or removed from public archives. Official statements cite calibration and processing issues, yet insiders report that raw files contained additional spectral features, later smoothed or hidden in the public release. Why these features were obscured is unclear. Was it a simple correction or something more deliberate? No authoritative source provides an explanation. Another peculiar observation involves the thermal emission of Atlas. Measurements from infrared instruments showed unexpected temperature variations across its surface. While officially attributed to rotation and uneven solar heating, a few anonymous researchers noted that the pattern of variation does not perfectly match a simple rotation model. Some speculate that subsurface structures or compositional layering could explain the anomaly. Others quietly entertain the idea that the object's properties may have been influenced by forces outside normal astrophysical processes. Taken together, these observations, unusual molecular ratios, exceptional structural integrity, rare compounds, and thermal anomalies, create a picture of Atlas as an object both familiar and profoundly strange. Whether these features are the natural result of interstellar formation and long-term travel, or evidence of unknown processes, remains unresolved. The composition of Atlas holds secrets that continue to challenge astronomers, inviting speculation, analysis, and wonder, while leaving gaps that may never be fully explained. The surface of 3I Atlas presents a fascinating puzzle. The fact is that spectroscopic observations in visible and near-infrared wavelengths indicate a predominantly icy exterior, with only a thin layer of dust and organic compounds. Most comets in the solar system have thicker dust mantles, which help insulate their volatile ices. Atlas, by contrast, shows remarkably exposed ice. The initial interpretation is straightforward. It may have formed in an environment colder than our outer solar system, preserving ice without the need for thick dust coverage. Yet the simplicity of this explanation leaves gaps, especially when considering the survival of Atlas through interstellar space. A curious detail lies in the molecular layering detected on the surface. Observations suggest alternating strata of volatile and less volatile ices. Water ice appears interspersed with carbon monoxide and traces of other compounds, forming a stratified structure that is unusual for comets in our neighborhood. Some scientists suggest this could result from repeated heating and cooling cycles during its interstellar journey, though the exact mechanism remains unclear. Others, speaking privately, wonder whether the layering might reflect intentional structural organization, though this remains speculative and unconfirmed. Atlas's reflection spectrum provides further anomalies. Its albedo, a measure of surface brightness, is lower than expected for such ice-rich bodies. This dimness hints at a coating of very fine particulate matter or a chemical alteration on the surface. Laboratory simulations suggest that cosmic ray exposure over millions of years could darken ices, but the uniformity of this effect is difficult to reconcile with random interstellar conditions. Some observers quietly speculate whether the surface may have been modified in a way that preserves the ice while altering its reflective properties, though no one has verified this publicly. Adding to the mystery are minor outgassing events. Unlike typical comets that produce plumes of gas and dust near the sun, Atlas exhibited very weak or intermittent activity. The gases released were primarily carbon monoxide, with water vapor appearing in negligible amounts. Official interpretations suggest the object had depleted most of its volatiles in earlier close stellar encounters. Yet some insiders note that the pattern of outgassing appears directionally aligned, almost as if the emission is channeled along specific axes. Could this reflect natural fissures and fractures, or something more deliberate? No definitive answer exists. Observation data also reveal thermal anomalies across the surface. Infrared readings show localized hotspots and cold regions that do not correspond neatly to the rotation period. Standard explanations attribute this to uneven surface composition or geometry. However, a few anonymous astronomers have noted that the pattern repeats across different observation campaigns, hinting at an unexpected uniformity in the anomalies. Some speculate this could indicate internal structures or density variations beneath the icy shell, though the evidence remains inconclusive. Finally, access to early compositional data was partially restricted. Some raw spectral readings were delayed or smoothed before release. Official explanations cite calibration issues, yet insiders hint that these data contained unusual peaks, potentially revealing rare or unexpected molecules. Whether these omissions were routine or deliberate is unknown. Taken together, the surface properties of Atlas, thin dust layers, stratified ices, low albedo, weak outgassing, and thermal anomalies, create a portrait of an object both familiar and alien. Whether these features reflect natural interstellar evolution or something more enigmatic remains unresolved. The icy exterior continues to guard secrets that challenge scientists and leave room for speculation. Spectroscopic studies of 3I Atlas have revealed molecules that, while chemically plausible, appear in ratios unfamiliar to solar system comets. The fact is that carbon monoxide, molecular nitrogen, and traces of complex organics have been detected, sometimes in quantities exceeding what is typical for comets formed around our Sun. Standard interpretations suggest that Atlas may have formed in a colder, more chemically diverse environment, possibly in the outskirts of a distant planetary system. Yet the unusual proportions, combined with the object's stability and composition, make some researchers pause. Minor anomalies were noted in the distribution of volatile compounds across the comet's surface. Water ice seemed concentrated in certain regions, while carbon monoxide dominated others, creating a patchwork of chemistry rather than a homogeneous mix. Some astronomers interpret this as evidence of differential sublimation, where lighter molecules migrated over millions of years. Others, speaking anonymously, speculate that the distribution could hint at processes not yet understood, perhaps a slow internal rearrangement or even subtle engineering, though this remains speculative and unproven. One curious aspect is the presence of trace hydrocarbons. Observations indicate small amounts of ethylene, methane, and other organics embedded in the ice matrix. While these molecules are known in comets, the relative ratios in Atlas differ from solar system norms. Some researchers suggest this reflects the chemical signature of a star system with a different metallicity, or possibly unique interstellar chemistry. In the community, whispers circulate that these organics could hint at prebiotic chemistry occurring outside our system, or more quietly, that the pattern may be too regular to be purely natural, though evidence is lacking. Thermal measurements revealed that sublimation of these volatiles occurred in unexpected sequences. Carbon monoxide, normally more volatile than water, sublimated unevenly across the surface. Some scientists attribute this to irregular layering, while others speculate about internal structures that channel or restrict gas flow. Infrared data also showed minor hotspots and cold patches, which did not correlate with visible rotation patterns. A few anonymous observers have suggested that the pattern is too consistent to be purely random, hinting at the possibility of internal mechanisms or structural differences that remain hidden from direct observation. Adding to the mystery, several early spectroscopic datasets were either delayed or partially redacted before public release. Official statements cited calibration and processing issues, yet insiders hint that raw spectra contained faint but unusual lines that did not match known chemical patterns. Why these lines were smoothed or removed is not documented. Some speculate that the missing information could have revealed unexpected molecules or unusual isotopic ratios, though no evidence has been confirmed. Finally, Atlas's minor dust particles also exhibited peculiar chemistry. Analysis from reflected light suggests a scarcity of silicates compared to typical comets, while carbon-rich compounds dominated. Some scientists argue this could indicate formation in an environment lacking significant rocky material, such as a distant, cold outer disk. Others quietly propose that the unusual composition may have been influenced by processes unknown to current astrophysics, leaving an open-ended question about whether Atlas's chemistry is natural or something more enigmatic. Taken together, the molecular and chemical data from Atlas paint a picture of a comet that is simultaneously familiar and alien. Its unusual ratios, patchy distribution of volatiles, trace organics, thermal anomalies, and unexplained data gaps create a puzzle that remains unsolved. Whether Atlas is simply a product of interstellar chemistry or a hint of processes beyond our current understanding is a question that continues to invite speculation and debate. Beyond molecular composition, 3I Atlas has revealed subtle isotopic anomalies that challenge conventional expectations. The fact is that preliminary spectroscopic analysis detected ratios of carbon, nitrogen, and oxygen isotopes that differ slightly from those commonly found in solar system comets. These variations are small, yet statistically significant, suggesting Atlas formed in an environment with a distinct chemical history. Officially, these differences are attributed to natural diversity among planetary systems, but the patterns themselves invite closer scrutiny. One particular anomaly involves carbon isotopes. The ratio of carbon-12 to carbon-13 appears lower than typical for comets originating in our neighborhood. The standard interpretation suggests formation in a star system with a different nucleosynthetic history, possibly one older or chemically unusual. Yet some researchers quietly note that the specific ratios resemble synthetic processes in laboratory simulations, though no evidence indicates Atlas is artificial. The resemblance is intriguing and has fueled subtle speculation. Nitrogen isotopes present a similarly puzzling picture. Measurements suggest a slight enrichment in nitrogen, 15 compared to solar system averages. While interstellar chemical evolution can produce such variations, the uniformity across Atlas's surface is surprising. Some astronomers suggest this could imply the comet's material remained isolated from external influences for millions of years, preserving its isotopic signature. Others, speaking privately, wonder whether such uniformity could hint at internal sorting or even deliberate stabilization of chemical composition. Again, speculative but thought-provoking. Oxygen isotopes also show minor deviations. The ratios of oxygen 16, -17, and -18 differ subtly from what is typical in comets formed around the Sun laboratory experiments. Suggest these ratios could result from prolonged exposure to cosmic rays in deep interstellar space. But the observed pattern is consistent across multiple measurements and does not perfectly match predicted models. Some insiders speculate this may indicate hidden internal processes, structural peculiarities, or exposure to unknown cosmic phenomena. The exact cause remains unverified. Adding to the mystery, some early isotopic data from high-resolution spectroscopy were temporarily removed from online archives. Officially, this was to correct calibration errors. However, insiders note that the removed data contained unusual peaks that could have clarified certain isotopic distributions. Why these peaks were smoothed or delayed before release is unexplained, leaving room for speculation about selective data handling. Was this purely procedural, or was there a more sensitive reason for limiting access? Another subtle clue comes from dust analysis. While major isotopes show unusual ratios, trace elements like magnesium and silicon appear in unexpected proportions, with slight depletion relative to carbon-rich compounds. Some scientists argue this may simply reflect formation in a carbon-rich outer disk. Others quietly suggest that the combination of isotopic and elemental anomalies is rare enough to invite speculation about processes that differ fundamentally from those observed in solar system comets. Taken together, the isotopic evidence paints a picture of 3I Atlas as a chemically distinct object, shaped by forces and histories outside our immediate experience. While natural explanations exist, gaps in the data, unusual uniformities, and minor anomalies leave room for speculation. Whether these isotopic signatures reveal an exotic origin, unknown interstellar processes, or something more enigmatic remains unresolved. The comet continues to guard its secrets, offering tantalizing hints that challenge scientists to rethink assumptions about interstellar chemistry. Beyond its ices and molecular composition, 3I Atlas has also revealed surprising information through its dust particles. The fact is that light scattered from Atlas indicates a predominance of fine carbonaceous grains, with surprisingly low amounts of silicate minerals compared to typical solar system comets. Standard interpretations suggest that Atlas formed in a region of its home system that was deficient in rocky material, perhaps in the outskirts of a protoplanetary disk. Yet the precise ratio of carbon to silicate particles is unusual and consistent across observations, raising subtle questions. Microscopic analysis of dust ejected from Atlas during minor sublimation events, inferred from photometric and polarimetric data, shows an unexpected uniformity. In many comets, dust grains are irregular in size and composition, reflecting random aggregation over time. Atlas, however, exhibits a narrow distribution of grain sizes, suggesting either formation under highly uniform conditions or selective survival during its interstellar journey. Some astronomers quietly speculate that this level of homogeneity could hint at internal processing mechanisms that are not natural, though evidence for this is purely circumstantial. Another intriguing detail involves the dust's reflectivity. The grains appear darker than expected for carbon-rich particles, absorbing more light and giving the comet a low albedo. Laboratory simulations suggest cosmic ray irradiation over millions of years could cause such darkening, but the uniformity of the effect across the surface is difficult to reconcile with random interstellar exposure. Some researchers whisper that the consistent darkness could result from processes beyond standard cosmic weathering, perhaps related to internal structures or unknown external influences. Atlas's dust tail, while weak, offers additional clues. The particles do not disperse as widely as expected for a small, fast-moving comet. Instead, they remain relatively cohesive, hinting at unusual particle interactions or electromagnetic effects. While officially attributed to low ejection velocity and the comet's small size, a few anonymous scientists have suggested that these interactions could hint at structural or even artificial properties that help maintain the dust coherence, though no data confirms this. Observation anomalies add another layer of intrigue. Early high-resolution imaging of Atlas's tail and coma was delayed in public release. Official statements cited processing and calibration issues, yet insiders hint that the original images contained subtle features, faint clumps, or unusual patterns in particle distribution that were smoothed before distribution. Why these data were altered or withheld is unexplained, leaving open the possibility that unusual dust behaviors were partially concealed. Finally, analysis of particle trajectories within the coma indicates minor deviations from expected ballistic motion. In some frames, grains appear to accelerate slightly in a direction inconsistent with solar radiation pressure alone. While this effect is extremely small and within observational uncertainty, several researchers have noted it privately as intriguing. Some speculate these deviations could reflect internal outgassing channels, electromagnetic interactions, or forces we do not yet fully understand. Taken together, Atlas's dust properties, uniform grain sizes, dark composition, cohesive tails, minor trajectory anomalies, and restricted data access, create a picture that is both scientifically fascinating and mysteriously elusive. Whether these features arise naturally from interstellar formation and travel, or hint at processes unknown or even artificial, remains unresolved. The comet continues to guard its secrets, leaving behind subtle clues that encourage careful observation, speculation, and wonder. 3I Atlas has offered intriguing insights through the faint gases it emits. The fact that spectroscopic measurements detected primarily carbon monoxide and traces of water vapor, while typical cometary volatiles such as methane, ammonia, or carbon dioxide were either absent or barely measurable. Standard interpretations suggest that much of Atlas's volatile inventory may have been depleted during previous stellar encounters or through long interstellar exposure. Yet the composition remains unusual enough to attract attention from planetary scientists and astrochemists alike. The distribution of emissions is another subtle anomaly. Observations indicate that the gases do not emerge uniformly across the surface. Instead, carbon monoxide appears concentrated in narrow regions, producing small, localized jets. Standard models attribute this to fissures in the ice crust or differential heating, but some researchers, speaking privately, note that the precision and orientation of these jets are striking. Could natural fissures alone create such organized emission patterns? Or might there be an unknown internal structure guiding the gas flow? No definitive answer exists, but the observations invite speculation. Atlas's weak water emissions further deepen the mystery. Unlike most comets approaching the Sun, where water sublimation dominates, Atlas shows minimal water release even at relatively close distances. This unusual ratio of carbon monoxide to water challenges simple thermal models. Some astronomers quietly suggest that the comet's interior may be unusually insulated or composed of exotic ices resistant to solar heating. Others hint that the pattern could reflect an interstellar design optimized for long-term preservation of volatiles, though this remains entirely speculative. Infrared and radio observations during outgassing events revealed minor hotspots correlated with the active jets. While thermal modeling suggests these should correspond to surface heating, some of the hotspots appear displaced relative to the sunlight angle, as if gas is channeled from subsurface regions. Anonymous sources from observatories confirm that these anomalies were noted in internal reports, but were not emphasized in public releases. Whether this reflects complex internal structure, unknown physical processes, or a simple observational artifact is unknown. Adding to the intrigue, access to early high-resolution spectra of gas emissions was temporarily restricted. Official statements cited calibration inconsistencies, but insiders hint that the raw data contained faint, unusual molecular lines that did not match known cometary emissions. Why these lines were smoothed or delayed before release remains unexplained, leaving a tantalizing gap. Could there be minor compounds present that are simply not part of our standard chemical catalog? Or were these spectral lines suppressed for other reasons? The answer is elusive. The directional coherence of the observed gas jets also raises subtle questions. In addition to orientation along fissures, some jets exhibit slight acceleration, anomalies not fully explained by sublimation physics. These minor deviations are too small to dramatically alter the orbit, but they appear consistently across independent observations. Some researchers whisper that the phenomenon may hint at internal density variations or electromagnetic effects influencing particle ejection, though concrete evidence is lacking. Taken together, Atlas's emissions, dominated by carbon monoxide, patchy and coherent jets, anomalous water ratios, thermal hotspots, and unexplained spectral lines, present a profile that is both scientifically rich and puzzling. Whether these features are entirely natural, the result of long interstellar evolution, or hint at processes not yet understood, remains open. The comet's subtle breath leaves hints for those who observe carefully, yet its secrets remain shrouded in interstellar cold and mystery. Beyond the expected ices, gases, and dust, 3I Atlas has revealed a series of subtle anomalies that continue to intrigue scientists. The fact is that several independent telescopes observed slight deviations in brightness, inconsistent with simple rotation models or predictable outgassing. These light curve variations are small, yet persistent, suggesting either an unusual shape, surface heterogeneity, or a combination of both. Official explanations favor a natural elongated shape, yet some astronomers quietly speculate that the regularity of the variations could hint at internal structures influencing light reflection. Another anomaly involves the polarization of reflected light. Measurements show an unusual alignment across the surface that does not perfectly match expectations for icy or dusty comets. Some scientists interpret this as evidence of aligned particles or specific surface textures. Others, speaking anonymously, suggest that the consistency may hint at material properties or arrangements not typically found in natural comets. While there is no concrete evidence of artificiality, the unusual polarization pattern fuels quiet speculation in certain research circles. Atlas's trajectory offers additional subtle puzzles. While the main hyperbolic orbit is well understood, small deviations from predicted positions were detected during its closest approach. These discrepancies were within measurement error, but repeated observations confirmed that the object's motion is slightly off the expected path in specific segments. Some researchers propose unknown forces acting on the body, perhaps interactions with interstellar gas or magnetic fields. Others, more cautiously, wonder if internal mass distribution or even structural peculiarities could explain the minor deviations, leaving room for speculative interpretation. Observational gaps add further intrigue. During periods of intense scrutiny, certain radar and spectral datasets were delayed, with officials citing routine maintenance. Anonymous insiders suggest that these gaps coincided with the detection of unusual emission or reflection features, which were later smoothed or partially removed in public datasets. Why the information was restricted is unexplained, sparking quiet speculation that something about Atlas's composition or behavior was deemed sensitive or anomalous. Infrared measurements also revealed subtle thermal fluctuations that did not correlate fully with rotation or solar heating. Some regions of the comet showed unexpected warmth, while others remained unusually cold, creating a patchwork pattern. Standard models suggest this may be caused by heterogeneity in surface ices or insulating layers of dust. Yet the uniform repetition of these anomalies across multiple observation campaigns has led a few astronomers, speaking privately, to entertain the possibility of hidden internal structures or unknown physical processes affecting heat distribution. Finally, there were faint indications of irregular outgassing directions. While the overall gas emissions aligned with expected sublimation models, minor deviations in the trajectory of ejected particles were detected. These anomalies are small but consistent, suggesting either subtle internal channels, uneven material distribution, or possibly unrecognized electromagnetic effects. Researchers have noted these phenomena in private discussions, yet public documentation treats them as minor curiosities. Taken together, Atlas's anomalies, light curve irregularities, unusual polarization, minor orbital deviations, thermal patchiness, and subtle outgassing quirks paint a portrait of an object both familiar and enigmatic. While natural explanations exist, gaps in the data, consistent irregularities, and unexplained phenomena leave room for speculation. Whether Atlas is merely a product of interstellar formation or something more extraordinary remains an open question. The comet's secrets continue to invite observation, debate, and wonder. Despite extensive observations, 3I Atlas continues to harbor secrets that challenge astronomers. The fact is that while its basic composition, orbit, and emissions are documented, many fine details remain ambiguous. Minor spectral lines, unusual isotopic ratios, and subtle structural features have yet to be fully explained. Official analyses attribute these anomalies to natural variability, long-term cosmic exposure, and observational limits. However, certain patterns continue to intrigue those who study the comet in depth. One particularly puzzling observation concerns faint features in the infrared spectrum. Some bands indicate the presence of uncommon molecules or slight chemical variations not typically observed in solar system comets. These lines were detected across multiple instruments and observation campaigns, yet some early datasets were temporarily withheld or smoothed in public releases. Anonymous researchers suggest that these hidden spectral details may point to rare compounds, unexpected isotopes, or even entirely unknown chemical processes. Why the information was initially restricted remains unexplained. Thermal imaging adds further mystery. Even after accounting for rotation and sunlight exposure, small regions of the surface exhibited inconsistent heating and cooling patterns. Officially, this is attributed to irregular surface composition or patchy dust coverage. Yet a few insiders quietly noted that the pattern repeats across independent observation campaigns, implying a structural or compositional uniformity not easily explained by random processes. Could these hotspots indicate layered ices, internal cavities, or forces yet unrecognized by current astrophysical models? The data are suggestive but inconclusive. Another subtle anomaly lies in Atlas's dust and particle behavior. Fine grains released during minor outgassing events did not disperse as widely as expected, and occasionally exhibited slight accelerations inconsistent with predicted solar radiation effects. Standard models attribute this to low ejection velocities or electromagnetic influences. However, some anonymous observers have speculated privately about the possibility of internal structures channeling the dust flow or other mechanisms, preserving particle cohesion over long distances. No evidence confirms these ideas, but the pattern persists. The comet's minor orbital deviations also remain a topic of discussion. While the hyperbolic trajectory is consistent with an interstellar origin, small deviations were recorded during close approaches to the Sun. Scientists suggest gravitational perturbations, interplanetary gas drag, or measurement uncertainties as explanations. Yet the fact that these deviations repeat subtly in multiple datasets raises questions. Could internal mass distribution or unknown forces account for them? The answer is not publicly established. Finally, gaps in observational coverage feed speculation. Certain radar and spectral measurements were unavailable for hours to days, coinciding with periods when unusual emissions or reflections might have been detected. Official explanations cite routine calibration or maintenance, but some insiders hint that the gaps may have hidden anomalous data. Why, if routine, were these intervals so precisely timed? No official explanation has been given. Taken together, 3I Atlas remains an enigma. Its composition, isotopes, thermal patterns, dust behavior, orbital subtleties, and restricted data all suggest a complex object whose secrets are only partially revealed. Whether these anomalies are natural consequences of interstellar evolution, the result of processes yet unknown, or hints of something more extraordinary, remains unresolved. The comet's mysteries continue to inspire scientific curiosity, speculation, and a sense of wonder, leaving observers with more questions than answers. The final truth about Atlas's nature is still waiting to be uncovered.